We'll do that same example now, only with actual values for the circuit elements and the source here. So again, the first thing we do is convert the time domain source to its phase representation and then calculate the impedances associated with the capacitor, resistance, and inductor here. So the phase representation of V, we'll call it cap V, or phasor V, is equal to 10 e to the j 30. Now, let's be explicit here. Omega is 1,000 radians per second. Radians per second. Z sub c is equal to 1 over j omega c, which is equal to 1 over j times omega, which is 1,000, times c, which is 10 times 10 to the minus 6, or 10 microfarads, and that then equals negative j 100 ohms. That's a negative j 100 ohms. Z sub R is just the value of the resistor, which is 50 ohms. And Z sub L is equal to j omega L, which is equal to j times omega, which is 1,000, times L, which is 75 millihenries. And that gives us a positive j 75. So this is a j 75 there. This is R is just equal to, or the impedance of that is equal to 50 ohms. And this, the impedance of the capacitor, is a negative j 100. We'll go ahead and define the current flowing through here, or the phasor representation of the current going through there, calling it phasor I. And let's write a Kirchhoff's voltage law equation going around that loop. Once again, adding up the voltage drops, so a voltage increase will be a negative. That would be a negative 10 e to the j 30, plus going across this capacitor, the voltage drop across that capacitor will be the current I times the impedance. So that will be I times the impedance, which is a negative j 100. Plus the voltage drop across the resistor is going to be I times 50. Plus the voltage drop across that inductor is going to be I times the impedance of that inductor, which is j 75. And the sum of those terms then equals 0. We want to solve for I, the current in this circuit. So we'll factor out the I from these common terms here and bring this term here on over to the other side, and we get then that I times a negative j 100 plus 50 plus j 75 is equal to a positive 10 e to the j 30. I have a negative j 100 plus j 75. That gives us a negative j 25 plus 50. Dividing both sides by that term then gives us that I is equal to 10 e to the j 30 divided by, writing the real part first, 50 minus j 25. You get out your calculator and you'll find that, well, first of all, let's convert just this denominator here to polar form. It's a little bit easier to see what's going on here if we do so. In polar form, that's equal to 55.9 e to the j, it's a negative j, 26.57. Now, we can see the division. It's 10 e to the j 30 divided by 55.9 e to the minus j 26.57. So 10 divided by 55.9 gives us the magnitude. The magnitude of the numerator divided by the magnitude of the denominator gives us 0.179. Now the phase, it'll be e to the j 30 in the numerator, e to the minus j 26.57 in the denominator. We've already demonstrated that when dividing numbers involving exponents, it's the exponent of the numerator minus the exponent of the denominator. So it's j 30 minus a minus that becomes plus a 26.57. That gives us a positive j 56.57. degrees. This then, this entire thing here, is the phasor representation of the current. We can now take this back into the time domain by recognizing that the amplitude of the current is going to be the magnitude of this phasor, or, let's be explicit now, I of t then is equal to amplitude of 1.179. It will be a cosine term. We came in as a cosine. We'll come back to the time domain as a cosine term. Cosine, the frequency doesn't change. That's still 1000 t. But now the phase of the current is equal to a 56.57 degrees. So plus 56.57 degrees. That then is the time domain expression for the current. The voltage, the source driving this circuit, is oscillating at 1,000 radians per second. The current is oscillating at 1,000 times per second. It's going back and forth, changing at the same frequency that the source is going into it. The source has an amplitude of 10 volts. The current flowing has an amplitude of 0.179 amps. So the amplitude of the current is smaller than the amplitude of the voltage. And finally, let's look at the phase. The phase angle of the voltage source is 30 degrees, positive 30 degrees. The angle of the current is 56.57 degrees. So we would say then that the current has been shifted ahead of the source by the 26.57 degrees. Here are plots of those. The voltage in the red, V of t, is equal to 10 cosine of 1000 t plus 30 degrees. I of t we have now found to be equal to 0.179 cosine of 1000 t plus 56.57 degrees. So here's the voltage. It's got an amplitude of 10 volts, and it has been shifted to the left by 30 degrees. The current has an amplitude of 0.179, and it has been shifted to the left 56.57 degrees. So the difference, I can draw this very well, I don't know if I can or not. That distance right there is a phase shift of the current ahead of the voltage. We say that the current is leading the voltage. The current peaks out before the voltage peaks. The current crosses the zero before the voltage crosses the zero. The current is leading the voltage by that much, which corresponds to, again, that 26.57 degrees. Just one note about what appears to be an inconsistency of units. And not only does it appear to be an inconsistency of units, it is an inconsistency of units. What are the units of omega, the radial frequency? That's 1,000 radians per second. Yet we're specifying the phase shift of 30 degrees. We're specifying it in degrees. To be consistent, and frankly, we're going to leave it in this form, I think simply because it's a lot easier for us to visualize. We have a better intuitive feel for phase shifts in terms of degrees than we do radians. But if we'd ever be doing calculations, we'd need to convert either this into degrees per second or change this to radians. Which, of course, to change your radians is going to just be simply the 30 degrees, the degrees times pi divided by 180. So that phase shift there, the 30-degree phase shift, represents pi sixth phase there. And similarly, you can do the same for the phase shift on the current. But the point is, and let's just drive this home, this circuit here, the circuit that we just analyzed, did not change the frequency. The frequency of the current flowing in here is the same as the frequency of the voltage. What did change was the amplitude and the phase. Using phasor analysis, we were able to determine the phase on the amplitude and phase of the current.